students, welcome back to Midha Guru. It's me Manan again, the maths faculty. Well, we launched a video called Trigonometry Part 1. Did you guys watch it till now? If you didn't, please go back and watch that video and then come back here. So in this video, we are going to cover the basics of what complementary angles are and how the trigonometric ratios of two complementary angles are related to each other. Apart from that, we are going to see a very broad topic known as the trigonometric identities. How they are derived, how we arrive at them, and how we are supposed to apply them in our problems. Well, without further ado, let's get into the lesson. Before we begin the video, those of you who haven't watched the Trigonometry Part 1, please go to our channel Midha Guru and watch the first part of this lesson, because there are many ideas and topics that if you don't understand, you won't be able to understand what we are going to cover in this lesson today. Before we get into the lesson, let us see what our aim to learn here is. The first is we'll take a basic understanding of what complementary angles are, although I am very sure most of you will know that. For those of you who don't, do not worry, I'll help you with it. Then we will see the relation between the trigonometric ratios of an angle and its complement. And the last is that we will understand how we derive and apply certain trigonometric identities, what they are, what their uses are, and how we are supposed to apply them. Well, without any further ado, let's get into the lesson. So before we go into the details, what are complementary angles? The shortest way to explain this is that if there are two angles A and B, the sum of A and B should be equal to 90 degrees. That is the definition of complementary angles. In this case, if A and B sum up to a 90 degrees, we say that A is the complement of B, and so far B is the complement of A. So let us see a few examples. For example, the angles 60 degree and 30 degree. When we add that, we get 90, which means that 60 is the complement of 30, and so 30 is also the complement of 60. The same goes for 45 degrees. A pair of 45 degrees are complements of each other. In the same way, any two angles, the sum of whose measures is equal to 90 degrees, can be called complementary angles and are complements of each other. Moving on, let's try and see what its relation is in trigonometric ratio. So now we'll try and see what the relation between the trigonometric ratios of certain complementary angles are. Before we begin, what is the relation between A and C? Well, we know by the angle sum property, the sum of the interior angles of a triangle should be equal to 180 degrees, right? Now we know that angle B is a right angle, so by substituting that value, now if we take 90 to the other side, it becomes a minus, and we are left with A plus C is equal to 90 degrees. So the measure of A and C summed up would give us 90 degrees, which is exactly the definition of complementary angles, which means that A is a complement of C and vice versa. So let us just start by calculating the trigonometric ratios for the two angles A and C. Now, if we look at it from the perspective of angle C, the perpendicular would be AB and the base would be BC. And when we look at it from the perspective of angle A, BC would be the perpendicular and AB would be the base. So the sine of C can be given by perpendicular by hypotenuse, or we can write that down as AB by AC. The cosine can be found by dividing the base by the hypotenuse, which we write as BC by AC. We can get the tangent for C by dividing the sine by the cosine, which gives us AB by BC. Coming to the cosecant of C, we know that it is the hypotenuse divided by the perpendicular, which gives us AC by AB. For the secant of angle C, we can just take the reciprocal of cos, which will become AC by BC. And to get the value of cotangent for C, we can just take the reciprocal of tan C, which gives us BC by AB. Now when we look at it from the viewpoint of angle A, the sine can be given by dividing the perpendicular by the hypotenuse, which gives us BC by AC. The cosine of A can be found by dividing the base by the hypotenuse, that is AB by AC. We can get the tangent by dividing this sine by the cosine, which gives us BC by AB. Now to calculate the value of the cosecant, we can just take the reciprocal of sine, which gives us AC by BC. In a similar fashion, to get the secant of A, we can take the reciprocal of cosine, which gives us AC by AB. And last but not least, we get the cotangent of A from the reciprocal of tan A, which is AB by BC. Coming back to this relation here, if A plus C is equal to 90 degrees, this would mean that C is equal to 90 minus A. Now coming back to these trigonometric values, if you can see that the sine of C and the cos of A are both equal. If we write that down, now if you look at the cosine of C and the sine of A, you can see that they are both equal as well, as it is BC by AC on both sides. So we can write that the cos of C is equal to the sine of A, or the sine of 90 minus C. If you look at the tangent of C and the cotangent of A, we see that they are both similar, or quite literally equal, as they are both AB by BC. Now coming to the cosecant, you can see that it is equal to the secant of angle A. The secant of angle C is equal to the cosecant of angle A. And the last, the cot of angle C is equal to the tangent of angle A. Now, if we look at the values that we wrote down here, we can clearly see that there is a relation between an angle and its complement. If C is the angle, then its complement would be 90 minus C, right? So the sine of C would be equal to the cosine of its complement. In the same way, the cosine of C would be equal to the sine of its complement. The tangent would be equal to the cotangent of its complement. In the same way, the cosecant of any angle would be equal to the secant of its complement. The secant of an angle would be equal to the cosecant of its complement. And last, the cotangent of any angle would be equal to the tangent of its complement. This is the relation between complementary angles and their trigonometric ratios. If you haven't understood well, please don't worry. As soon as you get into the exercise problems and solve a few, you will get a better hang of it. So, if you could open your NCERT textbooks to the exercise 8.3, we'll start solving it from the first problem. In the first problem, we are supposed to evaluate some values. Let us see. The first says sine 18 divided by cos 72. Let us just write this down. Now, just to tell you that the solution of complementary angles in trigonometry is not a one-way road. There can be two ways of solving it. We could either convert this sine of this angle into the cosine of its complement, or we could convert this cosine of this angle into the sine of its complement. Both these ways would be right. First of all, if we have 18 degrees, what would its complement be? So we know that 18 and 72 are complementary angles, as when we add them we will get 90. So instead of sine 18, I write down cosine of 90 minus 18. This will be equal to the cosine of 90 minus 18 being 72 divided by the cosine of 72. As both of them are common, we strike them out and we arrive at the answer 1. But hold on, if we converted this cosine into the sine of its complement, we would arrive at the same answer. And if you came to the answer by this way, please don't worry, your answer is not wrong. It's in fact right. These are two ways of solving the same problem. Moving on to the next one, we have tan 26 divided by cot 64. In a similar manner, let's just write the two angles. If we calculate the complement of said angle, we will get, so we can see that 26 and 64 are complements of each other. So now writing this problem down again, we get the tangent of 26 divided by the cotangent of 64 degrees. You can choose any one of these to convert to a function of its complementary angle. I choose the denominator. So we get the tangent of 26 degrees divided by the tangent of 90 minus 64, which would be the complement of this angle 64 degrees. And we know that 90 minus 64 is equal to 26. So we write down tangent of 26. As both of them are same, we strike them out and we get 1. So moving on to the next problem. In this one here, we have cosine of 48 degrees minus sine of 42 degrees. Again, if we calculate the complement of 48, we get 42 degrees. So these angles 48 and 42 are complements of each other. Let us convert this cos into the sine function of its complement. So we can write that down as sine 90 minus 48 minus the sine of 42 degrees. We get 90 minus 48 equal to sine of 42 degrees minus the sine of 42 degrees. As these are both same, we strike them out and arrive at our answer 0. Moving on to the next problem, we have the cosecant of 31 degrees minus the secant of 59. Again, following our pattern, if we calculate the complement of 31, we get, so 31 and 59 are complements of each other. So now when I write down cosecant of 31 degrees minus secant of 59 degrees, let's just convert this secant into the cosecant function of its complementary angle. We get cosecant of 31 minus the cosecant of the complement of 59, which we know will be equal to 31 degrees. Now as these both are same, we strike them out and arrive at our answer, which is 0. Moving on to the next problem. Here we are supposed to show the tan of 48 into tan of 23 into tan of 42 into the tan of 67 would be equal to 1. Let's see how we'll arrive at this. For this particular problem, first we calculate the complements of all these angles. The complement of 48 would be, and the complement of 23 would be, so now we see that 48 is a complement of 42 and 23 is a complement of 67. Now the next step would be to draw a reference triangle. Let us say that this angle here is theta Now to calculate the tangent of theta, we divide the perpendicular by its base, right? And to calculate the cotangent of this theta, we divide the base by its perpendicular. What happens when I multiply the tangent with the cotangent of the same angle? We get AB by BC into BC by AB. Or in a simpler way, if the cotangent is the reciprocal of tangent, we can write it as tan theta into 1 by tan theta, which means these two can be cancelled out. This means that if we multiply the tangent of a particular angle with the cotangent of the very same angle, we will always be equal to the product 1. Now, coming back to our problem. We leave the first two just as they are. Now, if we want to convert this tan into the cotangent of its complement, we get 90 minus 42. And we convert this tangent into the complement of its, the cotangent of its complement as well. We can see that this would be equal to the cotangent of 48 degrees and this would be equal to the cotangent of 23 degrees. As we arrived here, that when we multiply the tangent by the cotangent of the same angle, we will get 1, and so stands for 23 as well, which will be equal to 1. And hence, we just showed it. So let's move on to the next problem. Here we are supposed to show that the cosine of 38 into the cosine of 52 minus the sine of 38 into the sine of 52 will give us 0. Instead of changing any part in this first part, let us change both the sines in the second part to the cosine functions of their respective complementary angles. I will get cosine of 90 minus 38 into the cosine of 90 minus 52. So 90 minus 38 will give us 52 degrees and 90 minus 52 will give us 38 degrees. As you can see, both the sides are products of two similar numbers or values. So we can just cancel both of these out to get 0. So we just showed that cos 38 degree into cos 52 minus the sines of 38 and 52 produced will give us 0. Moving on to the next problem. Here we have an equation that says if tan 2a is equal to cot a minus 18 degree, where 2a is an acute angle, find the value of a. Let us see how we can solve this. If we want to convert this tangent function into the cotangent of its complement, we say the cot of 90 minus 2a. Now according to the question, this tangent of 2a should be equal to the cotangent of a minus 18. We write that down here as well. If all these three are equal to each other, this means that these two would be equal to each other as well, right? So the cot of 90 minus 2a is equal to the cot of a minus 18. As cot is a similar function, we can cancel it out on both sides of the equation. We get that 90 minus 2a is equal to a minus 18. Taking the 18 to this side and the 2 to the other, we get 3a is equal to 108 degrees, which means that a would be equal to 108 divided by 3, which gives us 36 degrees. So according to this problem, the value of this angle A would be 36 degrees. Moving on to the next problem, we have that if tan A is equal to cot B, prove that A plus B is equal to 90 degrees. For this, Let's draw a right triangle. We name these vertices as AB, and the vertex at which the right angle is C. This angle here is B and this angle here is A. What would the tan of A be? The tan of A is equal to the perpendicular divided by the base. Let's write that down as BC by AC. Now what would the cotangent of B be? The cotangent of B would be equal to the base by the perpendicular, which is also equal to BC by AC. Now we come to the fact that tan A is equal to cot B according to the question, which means that if I convert this tangent into the cotangent function of its complementary angle, I will get cotangent of 90 minus A is equal to the cotangent of B. As I said, the cotangents are similar functions. We cancel them out on both sides of the equation. We get that 90 minus A is equal to B. And then taking A to the right hand side, we get that 90 degree is equal to A plus B, which can also be written as A plus B is equal to 90 degrees. Hence, we prove that A plus B is equal to 90 degrees. The next problem says that if secant of 4A is equal to the cosecant of A minus 20, where 4A is an acute angle, find the value of A. Let us see how we can go about this. Just writing this down, we get secant of 4A is equal to the cosecant of A minus 20. Now if we want to convert this function secant into the cosecant function, we must take the complement of 4A. Meaning this is supposed to be written as cosecant of 90 minus 4A, which will be equal to the secant of 4A. This is equal to cosecant of A minus 20 degrees. As cosecant is a function, we can remove it on both sides of the equation. Now we get that 90 degrees minus 4A is equal to A minus 20 degrees. If we take 4A to the right hand side and bring this minus 20 to the left hand side, we get 110 degrees is equal to 5A, or A is equal to 110 divided by 5, which will give us nothing but that A is equal to 22 degrees. Okay kids, did you understand that well? If you didn't, please let me know in the comments down below and I'll try to explain it to you in a better way. Now in this next problem, it says that AB and C are the interior angles of a triangle ABC. We are supposed to prove that the sine of B plus C by 2 is equal to the cosine of A by 2. Before we begin, we know that by the angle sum property, the interior angles of a triangle are equal to 180 degrees. Now, if we take A to the other side, we get B plus C is equal to 180 degrees minus A. If we divide this whole equation by 2, we get that B plus C by 2 is equal to 90 minus A by 2. Now, as we know these two are angle measurements, we can apply trigonometric functions to them, right? So, if I apply sine, I get sine of B plus C by 2 is equal to the sine of 90 minus A by 2. Now we know that the sine of 90 minus any angle is equal to the cosecant of that particular angle. So replacing that value there, we get that sine of B plus C by 2 is equal to the cosine of A by 2, which is nothing but the proof that the problem requires us to show. So moving on to the next problem. Here it says that we are supposed to express sine 67 plus cos 75 in terms of t ratios of angles that have any value between 0 to 45. Let us see what we can do about it. We know that 67 and 75 do not lie in the bracket of 0 to 45. But there are angles related to 67 and 75 that do lie in this bracket, the name being their complements. So let's just calculate the complements of said angles. The complement of 67 degree would be 23 degrees and the complement of 75 would be 15 degrees. So now if we can just replace 75 by 90 minus 15 and 67 by 90 minus 23. We can write this down as sine of 90 minus 23 plus the cosine of 90 minus 15. We know that the sine of 90 minus any angle is equal to the cosine of this particular angle, and in the same way the cosine of 90 minus any angle is equal to the sine of said angle. So we can replace this as the cosine of 23 plus the sine of 15 degrees. So this is our answer. Moving on to the next topic. Okay students, we have arrived at a junction that is known as the trigonometric identities. Do you remember what identities in algebra were? Well, they were relations that helps us understand and solve problems related to algebra better. So are trigonometric identities. But what are these identities? Well, we look at them one by one. If you see this triangle ABC, you can clearly see that the right angle is at angle B. Let us consider this angle A to be an acute angle, and we'll calculate its trigonometric ratios. But before that, let's apply the Pythagoras theorem to this particular triangle. We know that the hypotenuse squared should be equal to the base squared, which summed up with the perpendicular squared. Let's just leave that like that. Now coming back to the trigonometric ratios. We know that the sine of A would be equal to CB divided by AC. Now if I square on both sides, right? And what about when I write the cosine of A? This is equal to the base divided by the hypotenuse, which can be written as AB by AC. Again, applying a square on both sides, I get AB squared by AC squared. What happens when I add the sine square of A plus the cosine square of A? I get CB squared by AC squared plus AB squared by AC squared. We can see that the denominators of these two fractions are the same. So we can just add them directly. We can write down that CB squared plus AB squared. Now the value of CB squared plus AB squared is quite clearly AC squared from the right triangle. So we just replace this by AC squared. This brings us to our first identity, that the sine square of any angle summed up with the cosine square of any angle is always equal to 1. We'll remember that and we'll move on to the next trigonometric identity. Moving on to the next identity, but before we begin, let's just write down the Pythagorean relationship for this right triangle, which is AC squared is equal to CB squared plus AB squared. Now, just look at this equation. If we divide this entire equation by AB squared, we get AC squared by AB squared is equal to CB squared by AB squared plus AB squared by AB squared. This is clearly equal to 1. Well, what are these two other fractions? If we look at AC by AB whole squared, we can get that AC by AB, that is the hypotenuse by the base, is nothing but the secant of said angle A. So we can write this down as the secant of angle A squared. In the same way, what would CB by AB mean? Well, it is equal to the tangent of said angle A. So we write that down as tangent A squared, and as we calculated this as 1. So the next trigonometric identity is that the secant squared of any angle is equal to the tangent squared of that angle plus 1. This is the second trigonometric identity. Moving on to the third and the last one. For this, let's again just write down the Pythagorean relationship for this particular right triangle, which is AC squared is equal to AB squared plus BC squared. Now if I divide this entire equation by BC squared, we get as you can clearly see, this can be cancelled out to get 1. Now again, looking at this right triangle, what is AC by BC equal to? AC is the hypotenuse and BC is the perpendicular. So AC by BC should give us the cosecant. So as the squared is applied on both the numerator and the denominator, we get that cosecant of A whole squared is equal to again AB by BC. Now what is AB by BC? It is the base divided by the perpendicular, which is nothing but the cotangent. So we write that down as the cot of A whole squared, and we arrived at this one. So the third and last identity is that the cosecant squared of any angle is equal to the cot squared plus 1. These three identities are very important in trigonometry and can be used in various amounts of topics to do a lot of mathematics. Well, let's apply this in our exercise problems, that is exercise 8.4. Let's get into it. Open your textbooks and your notebooks. And if there is a particular problem that you look at and you feel confident enough to solve it, you can pause this video and solve it step by step and later on see the video as a solution. Let's get into it. The first problem states that we are supposed to express sin A, secant A and tan A in terms of cotangent of A. I'll let you think about it for a minute while I have some water. So, any clues, kid? No? Don't worry, that's what I am here for. Okay, the easiest would be to express tan A, as we already know that it is a reciprocal of cotangent. So, tangent of A can be written as 1 by cotangent of A. Very easy, right? Well, the other ones won't be. We'll have to apply a bit of the trigonometric identities that we learnt a little bit earlier. Well, we know that the cotangent is written in the relationship as cotangent plus 1 is equal to the cosecant squared of A. Now we know that the cosecant is a reciprocal of sine. Let's write that down. So, 1 by sine squared A is equal to cot squared A plus 1. Now if we just take the reciprocals on both sides, we get sine squared A is equal to 1 by cot square A plus 1. And now removing the square, we get sin A is equal to plus or minus root over 1 by cot square A plus 1. In a similar fashion, we are supposed to express secant A as a function in cot A. Let us see what we can do about it. Using the same identity, or we can use a different identity as well, that is secant squared A is equal to tan squared A plus 1. We know that tan squared A is a reciprocal of cot squared A, right? So we write this down as secant squared A is equal to 1 by cot squared A plus 1. When we apply the LCM, we get 1 plus cot squared A by cot squared A. And when we remove the squared, we get plus or minus root over 1 plus cot square A by cot squared A. So these are the different ways of showing sin A, secant A and tan A in terms of the cotangent. Let's move on to the next problem. The second problem requires us to show all the t ratios of angle A in terms of the secant of A. Let us start with cos, as we know it is the simplest, as it is the reciprocal of secant A. Moving on to sin A. Let us write an identity related to sin A, which is that sin square A plus cos square A is equal to 1. As we just wrote, cos is the reciprocal of secant A. So let's just replace this value by 1 by secant square A. So sin squared A would be equal to 1 minus 1 by secant squared A. That is secant squared A minus 1 by secant squared A. Now on removing the square, we get that it would be equal so sin A in terms of secant A can be written as plus or minus root over secant square A minus 1 divided by secant A. Now we know an identity that links tan A and secant A directly. That identity is that secant squared A minus 1 is equal to the tan squared A. So on removing the square, we get that tan A is equal to plus or minus secant squared A minus 1. Now, for the cosecant of A, we can just use this value that we got for sin A. We know that cosecant A is equal to 1 by sin A. Now we got the value of sin A as this, so when we take its reciprocal, we get that cosecant of A is equal to plus or minus secant A divided by root over secant squared A minus 1. And the last one that we are supposed to prove, number 5, is the cotangent of A. Now we know that the cotangent of A is the reciprocal of tangent of A. So when I write cot A and write the reciprocal of the tan A I got here, I get that it is equal to plus or minus root over secant squared A minus 1. So this is how we can express all trigonometric ratios based on any one or two ratios. Let's move on to the next problem. Here in this problem, we are supposed to evaluate the value of sin squared 63 plus sin squared 27 divided by cos squared 17 plus cos squared 73. To solve this problem, you must have a fair idea of both identities as well as the topic that we covered earlier, that was complementary angles. Before doing anything, we know that 63 and 27 are complements of each other, as their sum is equal to 90 degrees, and so are 17 and 73 as well, which would mean that the sine of 27 can be written as the cos of its complement, that is the cosine of 63 degrees. And in the same way, the cosine of 73 can be written as the sine of its complement, that is nothing but the sine of 17. Excuse me. Now applying these values to said equation, we get sin square 63 plus sin square 27, which you can write as cos squared 63. And in the same way, we can write down cos squared 17 plus cos squared 73, which is equal to sin squared 17. Now we can see that this looks quite familiar, right? Well, it is nothing but the first trigonometric identity that we learned, that the sine squared of any angle summed up with the cos squared of any angle is always equal to 1. So we get 1. And down here it's the same, sin squared 17 plus cos squared 17, which would be equal to 1. So our answer will be 1. Moving on to the next problem. Now we are supposed to calculate the value of sin 25 into cos 65, cos 25 into sin 65. Now again, if I add 25 and 65, I get 90 degrees, which tells me that 25 and 65 are complements of each other. So before we do anything, let's just apply the complementary angle feature here. We get that sine of 25, and we can write cosine as a sine function of the complement of this angle, which is sine of 90 minus 65 degrees, plus the cosine of 25 into, instead of writing the sine of 65, I can write it as a cosine function of the complement of 65. As we just learned, the complement of 65 is 25. So I write this down as this becomes 25 degrees as well. Any number multiplied by itself is its square, right? So it becomes sine squared 25, and applying that same logic here, we get cos squared 25. This again is the first trigonometric identity that we learned, and we know that this will always be equal to 1. So this is our answer. Moving on to the next exercise problem. The next question is choose the correct option and justify your answers. We see here that 9 times secant squared a minus 9 times tangent squared a is equal to which of these? Well, before that, let's just see what happens if we take this out common. Do you remember this? If you don't, let's just see what the identity related to secant and tangent was. Well, if I take tangent to this side of the equation, I get that secant squared a minus tan squared a is equal to 1. And we can see that this is the same. So we just replace this value by 1 and we get the answer as 9. In the next, we are supposed to calculate the value of 1 plus tan theta plus secant theta into 1 plus cot theta minus cosecant theta. Well, we'll do a bit of shuffling. We know that tan theta is equal to sine by cosine of theta, and secant is equal to 1 by cosine. In the same way, cot is equal to cos theta by sin theta, and cosecant is equal to 1 by sin theta. Let's just apply all this to our equation here. We get 1 plus the value of tan theta being into when we do the addition of these fractions, we get, here the LCM would be cos theta, we get cos theta plus sin theta plus 1 into, when we take the LCM here as sin theta, we get sin theta plus cos theta minus 1. Now, if you can see and take this part as A and this part as B, and remember some of the algebraic identities we learned, this is clearly A plus B into A minus B, which would be nothing but A squared minus B squared. So we write that down as A being cos theta plus sin theta squared minus the square of 1, which will always be 1, and this can be written as cos theta into sin theta. Now when we expand this term, we get, if we treat this as A and B, we get A squared plus B squared plus 2 times of A into B, and we have a minus 1 at the end, and the denominator is nothing but sin theta into cos theta. Now we know that cosine plus sine squared is equal to 1. Writing that down as 1, we get, so this part becomes 1, writing the remaining as it is. As these two will cancel out, and we can see that the numerator and the denominator have the same part, sin theta into cos theta, we just cut that out and get the answer of 2. So that would be our answer. So in this one, we are supposed to find the value of secant A plus tan A into 1 minus sin A. Which of these ratios would it be? Well, let's just find out. We can write secant as 1 by cosine and tan as sine by cosine. So substituting these values here, we get 1 by cosine of A plus sin A by cosine of A into 1 minus sin A. As you can clearly see, the denominators are same, so we can just write this down as 1 plus sin A and 1 minus sin A. As you can see, this is another case of A plus B into A minus B, which you can get as 1 minus sin square A, which is nothing but A square minus B square divided by cos A. Now we know that 1 minus sin square A is equal to cos square A from the first identity. So we write that down as cos squared A by cos A. And we cut this cos and remove the power, we get the answer, the cosine of A. So this answer D will be correct. So here we have 1 plus tan square A divided by 1 plus cot square A. Well, if we substitute the value of tan square A with relation to cot square A, we get 1 plus 1 by cot square A, which is tan square A by 1 plus cot square A. Now taking the LCM as cot square A, we get cot square A and over that cot square A plus 1. Instead of dividing it by this, if we cross multiply by 1 plus cot square A, you can see that these two are quite similar, so we cancel them out. We get 1 by cot square A, which is nothing but tan square A. So this expression of 1 plus tan square A divided by 1 plus cot square A is equal to tan squared A. Well, moving on. In the next problem, we are supposed to prove that cosecant theta minus cot theta whole squared is equal to 1 minus cos theta by 1 plus cos theta. We'll go through this step by step. The first step is if we expand this bracket in the form of a minus b whole square, we get cosecant square, which is the a square, plus cot square theta, which is the b square, minus 2 times of ab, which is nothing but cosecant theta and cot theta. If you can just write this cosecant as 1 by sin square theta and cot as cos square theta by sin square theta minus 2 times of 1 by sin theta into cos theta by sin theta. Now, we can see that the denominators of all these three fractions are similar, so we can just do the arithmetic operation. That is 1 plus cos square theta minus 2 cos theta. The part up above here, you can clearly see, if I do this, it does not change the value, but you can see that it is in the form of a square plus b square minus 2ab. So we can write that down as a minus b whole square. And down under, sin square theta can be written as 1 minus cos square theta from the identity, that is sin square theta plus cos square theta is equal to 1. So we do that. We write 1 minus cos theta whole square divided by 1 minus cos square theta. If this is in the form of a square minus b square, we can write it as a plus b into a minus b. And this being a square, we can repeat it twice, writing in such a way. And as I said down under, we write a plus b into a minus b. Now 1 minus cos theta can get cancelled, and we get 1 minus cos theta by 1 plus cos theta, which is nothing but the right hand side of our equation. And hence, we have just proved that cosecant theta minus cot theta whole squared is equal to 1 minus cos theta by 1 plus cos theta. Moving on to the next exercise problem. So in the next problem, we are supposed to prove that cos a by 1 plus sin a plus 1 plus sin a by cos a is equal to 2 times of secant A. To add the two fractions, let's just take the LCM as cos A into 1 plus sin A. So up above we'll get cos A multiplied by cos A, which is cos squared A, plus 1 plus sin A into 1 plus sin A, which is 1 plus sin A whole squared. On expanding this bracket, we get A squared plus B squared plus 2 times of A into B. Now we know that cos squared A plus sin squared A is equal to 1. So we write that down as 1 plus 2 times of sin A by cos A into 1 plus sin A. Now we know that this will be 2 plus 2 sin A, and if we take out the 2 as common, we get 2 into 1 plus sin A divided by cos A into 1 plus sin A. Now we can cancel out 1 plus sin A and we get 2 into 1 by cos A. 1 by cos A can be written as secant A. Now this is the right hand side of our equation, and hence we just proved that cos A by 1 plus sin A plus 1 plus sin A by cos A is equal to twice of secant A. Moving on to the next exercise problem. So in this next problem, we are supposed to show that tan theta by 1 minus cot theta plus cot theta by 1 minus tan theta is equal to 1 plus the product of secant theta and cosecant theta. Let's start this. Now instead of tan theta, as you know, we can write sin theta by cos theta, and instead of cot theta, I can write cos theta by sin theta. Let's start by substituting those values. So we get sin theta by cos theta by 1 minus cos theta by sin theta plus cos theta by sin theta divided by 1 minus sin theta by cos theta. Now applying the LCM to both these separate fractions here, we get, up here we write sin theta by cos theta as it is, and we get sin theta minus cos theta by sin theta plus, we write this as it is and apply the LCM down here, we get cos theta minus sin theta divided by cos theta. Now when I do this cross multiplication, I get sin square theta by cos theta into sin theta minus cos theta plus cos square theta divided by sin theta into cos theta minus sin theta. Now as you can see, here we have sin theta minus cos theta, and here we have cos theta minus sin theta. To make them the same, I'll just take a minus sign common out of here. So this becomes sin square theta by cos theta into sin theta minus cos theta minus cos square theta sin theta into sin theta minus cos theta. Now I can take 1 by sin theta minus cos theta out as common. So I will get inside this bracket, I will be left with sin squared theta divided by cos theta minus cos squared theta divided by sin theta. Now again, on adding both or subtracting, in this case both these fractions, I get now as you can see here, up here I have sin cube theta minus cos cube theta. which I can further factorize as, I can write it as sin theta minus cos theta into sin square theta plus cos square theta plus sin theta into cos theta, and down here we have cos theta into sin theta. Now as you can see here, we have sin theta minus cos theta and we have the same here. So we can strike out both of these as they are common. And instead of sin square theta plus cos square theta, I can write down 1 plus cos theta into sin theta divided by cos theta into sin theta. If I write them as two separate fractions, I get 1 by cos theta into sin theta plus cos theta into sin theta by cos theta into sin theta. As both of these get cancelled out, now we have 1 by cos theta into sin theta, which you can write as 1 by cos theta into 1 by sin theta. Now we know that 1 by cos theta is secant theta and 1 by sin theta is cosecant theta. So now I come that this is equal to 1, and as I said, this will be equal to the product of secant theta into cosecant theta, which is nothing but our right hand side. So now let's move on to the next problem. So in this next problem here, we are supposed to prove that 1 plus sec A by sec A is equal to sin square A by 1 minus cos A. So let's just begin with the left hand side of this equation. We know that secant A can be written as its reciprocal in the form 1 by cos A. So we can write that 1 plus 1 by cos A divided by 1 by cos A, which further we get cos A plus 1 by cos A into cos A by 1. As I cross multiplied this fraction down here, I cancel both of these out and I get cos A plus 1. We leave the left hand side up till here. Now we operate on the right hand side. From the right hand side, as you can see, it's sin squared A. We can write that as 1 minus cos squared A divided by 1 minus cos A. If I just put a square here, it doesn't change the value, but it comes in the form of A square minus B square, which can be factorized as A plus B into A minus B. So I write that down as 1 plus cos A into 1 minus cos A and 1 minus cos A down under. So we cancel both of these out and we are left with 1 plus cos A. So as you can see, now we have equated that the left hand side and the right hand side are equal. So we just write down that LHS is equal to RHS. Hence our answer has been proved. So moving on to the next problem. So in this next problem, we are supposed to show that cos A minus sin A plus 1 divided by cos A plus sin A minus 1 is equal to cosecant A plus cot A. Now I just write this down in the same way, but with a minor difference. What I do here is I am going to divide both the numerator and the denominator of the left hand side by sin A. It does not change the overall value of the equation, but I can move a step ahead in the direction of the answer we require. And if I write all of these as separate fractions, I get something like cos A by sin A minus sin A by sin A plus 1 by sin A divided by cos A by sin A plus sin A by sin A minus 1 by sin A. Now I know that cos A by sin A is equal to cot A and 1 by sin A is equal to cosecant A, and the sin A by sin A will get cancelled out as 1. So rewriting this equation in the new form, I get cot A minus 1 plus cosecant A divided by cot A plus 1 minus cosecant A. Now instead of this 1 here, I will replace it by cot square A minus cosecant square A. As we know, the identity is cot square A is equal to 1 plus cosecant square A. So I get cot A minus cot square A minus cosecant square A plus cosecant A divided by cot A plus 1 minus cosecant A. So as you can see, this is in the form of A square minus B square. So we can reiterate it as A plus B into A minus B. So I get cot A plus cosecant A, let's just put this in a bracket, minus cot A plus cosecant A into cot A minus cosecant A. Now as you can see in the numerator, the two parts have cot A plus cosecant A as common. Taking that out, I get so inside the fraction I am left with 1 minus cot A, or in this case it becomes plus minus cosecant A divided by cot A plus 1 minus cosecant A. Now I know that this is cot A plus 1 minus cosecant A both in the numerator and the denominator. So I can just cancel both of them out. So I will be left with the answer cot A plus cosecant A, which is nothing but our right hand side. So moving on to the next problem. So in this next problem, we have root over 1 plus sin A divided by 1 minus sin A should be equal to secant A plus tan A. Let's start. We write as 1 plus sin A by 1 minus sin A. As in the last problem, we are going to do some division both to the numerator and the denominator here too. But in this case, we'll divide it by cos. So what I am aiming at is I'll get 1 by cos A plus 1 by, sin A by cos A divided by 1 by cos A minus 1 by or sin A by cos A. Now I know that 1 by cos A can be written as secant A and sin A by cos A can be written as tan A. So writing that down, I get secant A plus tan A by secant A minus tan A. Now if we just rationalize the denominator, to rationalize it, as this is in the form of A minus B, I'll multiply it by A plus B. So if I multiply the denominator, I'm supposed to multiply the numerator as well, right? So now I get secant A plus tan A. As this is both A plus B, I get secant A plus tan A whole squared. And here I'll get secant square A minus tan square A. Now from the identity secant square A is equal to 1 plus tan square A, I can get that this will be equal to 1. So I can remove the root as this is a square and this is a root, and I'll get secant A plus tan A, which is our right hand side. Now moving on to the next problem. So in this next problem, I have to prove that sin theta minus 2 sin cube theta by 2 cos cube theta minus cos theta is equal to tan theta. So I just write down the left hand side. I get cube theta by 2 cos cube theta minus cos theta. So in the numerator, I take out sin theta as common from both the terms, and in the denominator, I take out cos theta as common from both the terms. I get Now I know that sine square theta plus cos square theta is equal to 1. So instead of sine square theta, I can write it as 1 minus cos square theta. So I get we know that sine theta by cos theta is equal to tan theta. Now coming inside the bracket, when I open this bracket right here, I get 1 minus 2 plus 2 cos squared theta divided by 2 cos squared theta minus 1. So 1 minus 2 will become minus 1, and we can rewrite this as tan theta into 2 cos squared theta minus 1 by 2 cos squared theta minus 1. Now I can cancel both of these out as they're common, and I get the answer, or the right hand side in this case, tan theta, which is equal to our question. So moving on to the next problem. So in this question right here, we are supposed to prove that the sine plus cosecant A, sine A plus cosecant A whole squared plus cos A plus secant A whole squared is equal to 7 plus tan square A plus cot square A. Let's just do the algebraic expansion of both these terms. Here we'll get sine squared A plus cosecant squared A plus 2 times of sine A into cosecant A, plus we open this, we get cos squared A plus secant squared A plus 2 times of cos A secant A. Now we know that sine A and cosecant A are each other's reciprocals, which means cosecant A would be 1 by sine A, so we can just strike them out. And in the same way, cos A and secant A are related in the same way, so we can strike them out as well. On rewriting this, I get 2 plus 2, which is 4, plus sine square A plus cos square A plus cosecant square A plus secant square A. Now I know that sine square A plus cos square A is equal to 1. So I get 4 plus 1 from here plus cosecant squared A plus secant squared A, which is 5 plus. Now instead of cosecant squared A, I can write that down as 1 plus cot squared A, and instead of secant squared A, I can write down from the identity 1 plus tan squared A. Now in the end, I get 5 plus 1 plus 1, which is 7, plus cot squared A plus tan squared A, which is nothing but our right hand side. So now moving on to the next problem. Now in this next problem, I am supposed to show that cosecant A minus sine A into secant A minus cos A is equal to 1 by tan A plus cot A. Let's go about this. If I write down cosecant A minus sine A as 1 minus sine A, 1 by sine A minus sine A, and in the same way 1 by cos A minus cos A, I get 1 minus sine squared A by sine A into 1 minus cos squared A by cos A. So I can write down 1 minus sine squared A as cos squared A, and in the same way 1 minus cos squared A as sine squared A. So I get cos squared A into sine squared A divided by sine A into cos A. As I can strike the powers out here, I get cos A plus cos A into sine A. Let's leave the LHS here. This was our left hand side. Now coming to the right hand side, I get 1 by, instead of tan A, I can write sine A by cos A, and in the same way for cot A, I can substitute it by cos A by sine A. So I write down sine A by cos A plus cos A by sine A. Taking the LCM here, I get 1 by sine squared A plus cos squared A divided by sine A into cos A, or cos A into sin A divided by sin square A plus cos square A. Now our denominator is nothing but the first identity that we learnt and will be equal to 1. So we will be left with cos A into sin A. Now as you can see, our left hand side and right hand side of this equation are both equal. So we know that our proof has been completed. So now moving on to the next and the final problem. Now in this next problem, we are supposed to do two proofs. That is, first we must prove that this is equal to tan squared A, and in the second we must also prove that this is also equal to tan squared A. So let's begin with the first part. I have 1 plus tan squared A divided by 1 plus cot squared A, which I can also write as a reciprocal, which is 1 by tan squared A. Now in the denominator, if I take the LCM, I get now when I cross multiply this, I get 1 plus tan squared A by 1 into tan squared A by tan squared A plus 1. As both of these are equal, I cancel them out and I come to tan squared A. So this is equal to tan squared A. Now let's come to the second part. In a similar fashion, I can just write this down as in the same way I'll get here, if I take minus as common, I will get again, instead of division, I'll do the cross multiplication, which would look something like this. As these both are common, I'll just strike them out and I'll be left with minus tan A whole squared, which will be nothing but tan squared A. So now we can see that all three parts of this equation are equal to each other. So students, we have come to the end of our lesson for today, but do not worry. We have another video coming very soon dealing with some applications of trigonometry, which is all about the heights and distances. So stay tuned for that video. And if you haven't yet subscribed, please subscribe to our channel Midha Guru and join the family today. Thank you.